1.4 Power and roots. Definition. In general, we say W is an n fruit of a non-zero complex number Z if W to the nth power is equal to Z, right? Well, that is basically, well, if you take the nth root, right, of Z is equal to nth root of Z, that is equal to W, right? No, sorry, nth root of W to the n, that is equal to W, right? Yeah, and now let's start with a definition. Just to now, suppose Z is equal to R cosine theta plus sine theta, and W is equal to rho cosine of phi plus sine phi, right? So that is theorem. Suppose roots. Suppose Z is equal to R cosine theta plus I sine theta, right? And W is equal to, well, rho, you have cosine phi plus I sine phi, right? Are polar forms of the complex numbers Z and W, right? And then we can write it as, well, then the WK, the nth root, right? Really, WK, then WK is equal to, well, the nth root of R, right? And then you have cosine of 2k pi n plus I sine of theta plus 2k pi n for any n, really. Well, n for n, that is for n, that is well, natural number. No, we well, 0, 1, 2 up to n minus 1, right? And well, now let's prove it. So really, if we would raise, we know by definition W to the n power is equal to Z, right? Well, then W to the n power really just equal to rho n, you have cosine n phi plus I sine n phi. Well, that is equal to Z, right? What is Z? Z is R cosine theta plus I sine theta, right? And well, we may conclude that, well, if we do compare the two, you get, well, rho n has equal to R, right? And cosine n phi plus I sine n phi is equal to, well, cosine of theta, n theta, really. Oh, sorry, no, not n theta. Well, it's only theta plus I sine of theta, right? And now we will then, by this equation, right, we can do rho is equal to the nth root of R. We take the nth root of both sides, and we know that cosine of n phi is equal to cosine of theta, and you know, sine of n phi is equal to sine theta, right? And well, how about we just set them equal to each other? So we have n phi is equal to theta, right? But note that you can always add 2k pi pi to it because, well, it's a circle, right? So, well, now we can solve for we can solve for phi, and then we have theta plus 2k pi over n, right? For, well, k can be 0, k is equal to 0, and you have 1, and n minus 1, right? And, well, how about we let k is equal to it's equal to n plus m, then phi really becomes theta plus 2m plus n pi over n, right? Well, since we have m, the reason why we set it equal to n and m, because we need something to cancel n, so we can really just factor it out, right? No, we can split the fraction, because if k is not determinate, then you can't really factor it. You can only write it as a fraction, right? So now we have n in there. We can combine like terms, right? Really, it's just 2m pi divided by n, and then you have n cancel of n. You have 2 pi, right? Plus 2 pi. Now, well, let's combine them together. Well, that is, well, sine of theta, right? Well, if you substitute theta, we just solve for theta over here, right? Now we can have sine of, well, we have sine of theta plus 2m pi n, right? And we can set n equal to, we can set this term equal to 0, right? Because it's really, at 2 pi is really the same thing. So now we just found the minimum, right? And cosine of phi is equal to theta plus 2m pi n, right? Because if you add 2 pi over here, it's the same thing. And now we know. Now we may conclude, if you substitute back in over here, you get double k, and the k is the kth root. I think this is the kth root, because not the kth root. You know how if you take a square root, you have positive and negative, right? So you have two roots, right? So k, that's what k is. So I think it's better if we do an example, right? So that basically you have to find all the k's, right? No, you have to find all the possible roots, and well, let's say if we have z equals to I, right? So, well, let's solve the equation for w cubed is equal to I, right? So now we want to take the cube root, right? So what are the possible cube roots? Well, with r is equal to 1, and you have, well, theta equal to argument of I, that is equal to pi over 2, right? And, well, that implies, well, since r is equal to 1, right, so z is equal to, the polar representation is equal to cosine of pi over 2 plus I sine pi over 2, right? And n is equal to 3. And now we have the formula. Let's write it again. So that is equal to cube root of 1. You have cosine of, well, theta, that's pi over 2, plus 2k pi 3 plus I sine of pi over 2 plus 2k pi over 3, and brackets, well, k goes up to 2, right? Because that's n minus 1. And now, if we would just gently plug in what k is equal to, well, I think we can fit 1 over here. Let k go to 0, well, that is equal to w naught equal to cosine pi over 6 plus I sine of pi over 6 is equal to root 3 over 2 plus 1 over 2 I, and we have k equals to 1, right? And you have w1 that is equal to cosine of 5 pi over 6 plus I sine 5 pi over 6, that is equal to negative root 3 over 2 plus 1.5 I, right? And if we finally let k equal to 2, we have w2 that is equal to cosine of 3 pi over 2 plus I sine of 3 pi over 2 is equal to negative I. Right, so now we've resolved it. And, well, now we want to find the principal end fruit, right? So now theorem, right? The unique root of a complex number z obtained by first bracket over here, obtained by using the principal value of argument of z, right, with k equal to 0, right? Well, this part is really just argument of z, the principal value. Right? It's referred as the principal end fruit of w. Well, let's do another short example, right? For example, well, we know from example 1, right, we know z is equal to I, then we have the principal value of z, principal value of I, that is equal to pi over 2, right? And we see that, well, w naught is equal to root 3 over 2 plus 1 over 2I, right, is the principal cube root of I, right? Of maybe this will be more clear, of z equal to I, right? So the choice of argument of z, well, principal value of argument of z, and k equal to 1 guarantees us that when z is a positive real number r, the principal end fruit is, well, really just end fruit, right? So we can write a corollary if this is not mentioned in the textbook, but I summarize it. I think this point deserves to be highlighted, right? The choice of argument z and k0 guarantees when z is a positive real number r, then the principal end fruit is the end fruit of r, right? And now example 3. Well, if z is equal to 1 plus I, really, then in this case r is equal to root 2, theta is equal to argument of z, well, that is equal to power of 4. That's also equal to the principal argument of z, right? And we know, since we're finding the fourth root, right, really we get fourth root, right? We want to find the fourth root of, we want to find, fourth root. Well, how about we write like this, right? So n is equal to 4, right? And now if we write the formula, this is equal to fourth root of 2, and you have cosine of pi over 4 plus 2k pi over 4, that's the n, right? And plus I sine of pi over 4 plus 2k pi over 4, right? And k is equal to, well, start from 0, goes up to 3, right? 2, 3, that's n minus 1. So now we want to do k equal to 0, that's equal to w naught, that is equal to fourth root of 2, cosine of pi over 16 plus I sine pi over 16. That is about 1.1664 plus 0.2320 I, right? And k is equal to 1, w1 is equal to root 2 cosine of 9 pi over 16 plus I sine 9 pi of 16. That is equal, roughly, that's about negative 0.2320 plus 1.1664 I, right? And then let k equal to 2. Well, that gives us w2 root 2, and cosine of 17 pi over 16 plus I sine of 17 pi over 16. That is about 1.1664 minus 0.320. Now I think we can recognize the pattern over here, really. This is equal to 4 root 2 cosine of 25 pi over 16 plus I sine of 25 pi over 16. That is about, well, really that's 2.2320 minus 1.664 I. Really, I think we have discovered a pattern now. Now let's end it with a remark. When m and n are positive integers, with no common factor, then we define the rational power of z really is just z m divided by n, right? Well, that's equal to, this is really simple, z to the m power 1 over n. There, right? And now let's do one of the exercises, extension. So the textbook ends here, but I would do some extra practices just on my courtesy, right? And now extension. Now let's definition. The n distinct nth root root of unity. The nth root of unity. Sketches the regular polygons formed with oh, sorry, I copied the wrong line. That is very funny. I just realized. Right. Are the solutions of the equation, Wn is equal to 1, right? So now let's do an example. Well, example 4. What is example 4? Example 4 is exercise 19, right? Exercise 19, right? So, well, we start from this. Given cosine of 2 pi k of n plus sine of 2 pi k n, right? And we know that w is a cube root. Unity corresponding to k is equal to 1, right? And solution, really just substitute n is equal to 3 and k is equal to 1, right? So now we have w is equal to, well, because we're trying to find, so sorry, I think I'm not being clear enough. Well, part B says replace n equals 3, n equals 4, n equals 5. So now we want to calculate that, right? So now given, we really have to solve for these, n equals 4, n equals 5, right? So let's do part B. Part B, right? So you substitute. So you have cosine of 2 pi 3 plus I sine 2 pi 3. Well, that is equal to negative 1/2 plus root 3 over 2 I, right? And now let's do w over 2, right? Use the De Moivre's formula, right? Then really we can find this 2, that is equal to cosine of 4 pi over 3 plus I sine of 4 pi over 3. Well, that is equal to negative 1/2 minus root 3 over 2I, right? And how about we substitute? We know w, right? We know w square, right? So how about w plus w square, right? That is equal to negative 1, right? And that is B, right? And then now number 3 wants us to plot the roots of unity formed by part B, well, which is something that we have to resolve, and sketch the regular polygon formed by the vertices. Well, let's see. Well, anyways, that's. I don't think we can sketch over here really. Anyways, let's do part C. We can do like this. Minus y3, that is equal to, well, if we do the difference of square, right, that's addition plus plus, right? So the minus is in the front, right? Well then, if w cubed is equal to 1, right, then, well, if we w cubed minus 1, that's equal to 0, right? That is w minus 1, and you have w squared plus w plus 1, that is equal to 0, right? Then that means it's either w minus 1 is equal to 0, or w squared plus w plus 1 equal to 0. But didn't we just say w plus w squared is equal to -1, right? And then you plus, so, well, we can just substitute -1 plus 1 is equal to 0. So now the proof is complete, right? And that is chapter 1.4.